Let us solve few problems on the fundamentals of single phase transformers. We will split the tutorial problems on transformers under different categories. The first category that we are taking is on fundamentals and the EMF equation. The problem number 1, we have a transformer which is given a rating of 3000 by 200 volt, 50 Hz, single phase transformer. The cross-sectional area of the core is given to be 150 centimeters square for the core. If the number of turns of the low voltage winding is 80, determine the number of turns on the high voltage winding and maximum value of flux density in the core. We have to note here few important concepts. First, the rating of the transformer that is given to in the problem is just a representation of the transformation ratio K. So it means that it is given in the form of E1 by E2. We know that V1 by V2 are basically the supply voltage and the load voltage. E1 and E2 are the induced EMF. So the first thing that to be noted is that whenever the rating of the transformer is given as the voltage rating as 3000 by 200 volt, the ratings are usually given in the form of E1 by E2 and not V1 by V2. Second thing is, the first data that is given in the voltage rating correspond to the primary winding where the source is connected, and the second one is correspond to the secondary winding where the load is connected. Also, these ratings we have to understand which one is the low voltage side and which one is high voltage side. Like in this particular problem, the 3000 volt is basically the high voltage side and 200 volt is basically the low voltage side. So the primary winding here is the high voltage side and the secondary winding here is the low voltage side. Many a times in the problem, it may be mentioned that the supply voltage is given either on the high voltage side or on the low voltage side. So that will become the primary winding. But however, if not mentioned explicitly, then we have to consider that the first data, whatever is given, here in this problem, we'll take the example 3000 by 200. So this one is the representation of E1 and 200 volt is the representation of E2. First thing. Second thing, the 3000 volt is basically the high voltage winding, 200 volt is basically the low voltage winding. Third, this high voltage winding is basically the primary winding and the low voltage winding is basically the secondary winding of the transformer. So let us see how to solve the problem. So given the induced EMF E1, E2, the frequency of the supply is given to be 50 Hz and the cross-sectional area of the core in meters square we have to convert, that is 150 into 10 to the power minus 4 meters square. Now the number of turns are given on the low voltage side, that is 200 volt side, that is 80. So we can say that is N2 is given to be 80. And we have to find what is the number of turns on the high voltage side, that is basically N1, and maximum value of flux density. Now phi represent the flux and Bm represent the flux density. So whenever we need to determine the flux, we have to determine the phi whose unit is in Weber, and whenever we need to find the flux density, that is Bm, the unit will be in Weber per meter square or it is in Tesla. So we have to read the question carefully to determine what value is asked. So here it is as flux density, it means Bm we need to find. So the solution to find the number of turns on the high voltage side, we can find out from the EMF per turn concept. So we know that EMF per turn is constant, where we can say that E2 by E1 is equal to N2 by N1. It means that we can put the value 200 by 3000 is equal to 80 by N1, and hence we can easily find out what is the value of N1. N1 is equal to 1200. So 1200 turns are there in the high voltage side of the transformer. Now, if we need to find what is the maximum value of flux density, we can use the EMF equation of the transformer, which is 4.44 frequency into phi m into N1. This phi m we can write in the form of Bm into area. So we know that the maximum flux is equal to the maximum flux density multiplied with the area of the core. We can determine this EMF equation from the secondary side as well. So when we are taking the secondary EMF, then the number of turns we have to take N2. If we are taking E1, then the number of turns we have to take N1. Rest the formula will remain the same, that is 4.44 frequency into Bm into area. And then we can multiply either with N1 or N2 to get E1 or E2. Once we substitute the value of E1 and the other data, the only unknown data is Bm, which we need to find. So Bm we can easily find as 0.75 Weber per meter square. So this is the maximum value of the flux density. Next problem, here we have to find for a single phase 50 Hz transformer 80 turns on the primary winding and 280 turns in the secondary winding is given. So the word primary is used, that is the side where the source is connected, and the secondary winding, the side where the load is connected. The voltage applied across the primary winding is 240 volt and at 50 Hz. Calculate the maximum flux density in the core, induced EMF in the secondary side. The net cross-sectional area of the core is 200 centimeters square. So we need to find what is the maximum flux density Bm as well as the induced EMF on the secondary side. So secondary side means E2. Now let us check the given data. So we have been given the frequency, number of turns on the primary side, number of turns on the secondary side, the voltage on the primary side, and the cross-sectional area. So here it is written that 240 volt is the applied voltage on the primary winding. So we have taken V1 is equal to 240 volt. Now for an ideal transformer, we know that V1 and E1 are equal. That is equal to 240 volt in this particular case. Hence, we can use the EMF equation E1 concept, 4.44 frequency multiplied with flux and the number of turns. And hence, we can substitute 240 volt in the induced EMF E1, which is 240. Hence, we can get the unknown quantity, that is the maximum value of the flux density, equal to 0.68 Weber per meter square. Now the induced EMF in the secondary, again now we can find out in terms of the EMF per turn concept, where the unknown quantity, that is the secondary EMF, we can easily find out because the number of turns are given in the primary side and the secondary side. So E2 is equal to 840 volt. In the third problem, where we have a transformer 80 kVA, the voltage rating is given 3200 by 400 volt, 50 Hz, and the turns given is 111 turns on the secondary winding. The number of turns on the primary winding we have to determine, that is we have to determine the N1, the secondary current, what is the current flowing in the secondary, I2, the cross-sectional area of the core, so we have to find what is the cross-sectional area of the core, given that flux density is 1.2 Tesla. Now note here, the current whatever we are finding I2, it is basically the full load current we are going to find, because we will be finding this current with respect to the full load kVA rating of the transformer. So the current whatever we are going to find here is the full load current. So all the data whatever is given, we will note down first the kVA rating, E1, E2, the frequency of the supply, the number of turns on the secondary winding, and the flux density. Now the number of turns on the primary winding we can obtain from the EMF per turn concept, E2 by E1 is equal to N2 by N1 concept, and hence we can find out that the number of turns on the primary side is equal to 888. Hence, the secondary current we can find from the ideal transformer point of concept, that is V2 is equal to E2 and the kVA rating. So we know that the current we can find out from the kVA rating of a transformer as kVA rating multiplied with 1000 divided by the voltage. Since we are finding the secondary current, so we have to take the secondary voltage in the denominator. So here we have the 80 kVA transformer and 400 volt on the secondary side. Hence 200 ampere is the current which is flowing on the secondary side. The cross-sectional area of the core we can get it from the EMF equation of the transformer. Hence all data are given here. Only unknown quantity is the cross-sectional area in the EMF equation. So easily we can put it in the EMF equation. With all known quantities, we will find that cross-sectional area is 135 centimeter square. The next topic that we are going to take is basically dependent on the core losses and the no load operation of the transformer. So here we will not include anything on the copper loss. So we will not take copper loss, we'll take only core losses into account, and the transformer will be under no load operation. So the transformer 50 kVA 2300 by 230 volt 50 hertz transformer is taking 200 watt at 0.3 amps at no load. So that there is no load on the transformer and the power is 200 watt. So this is the input power of the transformer. When 2300 volt is applied to the high voltage side. So if we see here, it can be observed that the transformer rating E1 by E2 and the voltage is applied as 2300 volt on the E1 side. That is the primary side. So this transformer is an ideal transformer where E1 is equal to V1 and the primary resistance is given 3.5 ohms. We have to determine the core loss and the no load power factor. So one thing to be noted here is that under the no load condition of the transformer, whatever the power is shown in the wattmeter, that is the representation of the core loss only. But in this problem, we are going to take the primary resistance also into account and see what we are going to get. So the input power, the input voltage, the no load current and the primary resistances are the data given in the problem. Core loss we have to find. So the copper loss in the primary side we can take as I0 square R1. What is I0? I0 is the no load component of the current in the primary side. So the primary current I1 is equal to I0. That is the no load current. So which is 0.315. Now note here, these data is very less, close to 0. So even we neglect the copper loss in the primary side under no load condition, we'll get not much difference in the answer. So core loss is equal to input power minus copper loss, and the input power is 200 watt and the copper loss we are getting 0.315. So the core loss is equal to 199.685. Now note here, this 200 watt the input power and the core loss we are getting 199.68. It means that the copper loss in the primary side we can neglect and directly we can say that whatever the wattmeter reading is showing under the no load condition, that is basically the core loss only. However, in this problem, we have solved it and proved that yes, the wattmeter reading is the core loss only. Now, the power factor under no load condition we can find out from the reading of the wattmeter. So, wattmeter reading is equal to VI cos phi, where we have the primary voltage, no load current and cos phi naught. That is the power factor under the no load condition. That is what we have to find. All data are given except the power factor which we need to find. So it is 0.29 lagging in nature. So we have to substitute the known quantities and find out the power factor under the no load condition. Problem number 5th, where we have 230 by 110 volt single phase transformer. It is taking an input of 350 volt ampere at no load condition and at rated voltage. Now note here, if we're talking about the input side, so input side is the 230 volt side. So that is what at the rated voltage we are taking, and 350 volt ampere is the apparent power which is taken at the no load condition. So the core loss is 110 watt. Find the no load power factor, the iron loss component of the no load current. So in theory we have seen that the current I0 has two components. One component is IW component, which is the working component, and another current is I mu component, which is the magnetizing component. So if we are drawing in terms of the phasor, we have seen that the flux we can take on is the reference and V1 we can take at the y-axis. So the no load component of the current I0 can be resolved into two different components of the current. The current in the direction of phi will be I mu and the current in the direction of V1 will be IW, and this angle will be equal to phi naught. So when we are trying to find the power factor, we are basically finding the cos phi naught component. So here the iron loss component is basically the IW component and the magnetizing component is basically I mu component. So the data that are given is basically the apparent power or the kVA rating of the transformer under the no load condition, the iron loss or the input power, and the induced EMF on the primary side. So we can use that V1 I naught is equal to the kVA rating, and we can also say that V1 is equal to E1, so it is equal to E1 I naught. The only unknown quantity here is that we are not knowing what is the value of I naught. So I naught we can find out from this equation. Now power is basically V1 I naught cos phi naught, where all data are given except the value of cos phi naught. So that is the no load power factor, which comes to be 0.314, lagging in nature. Now iron loss component of the no load current is IW, which is equal to I naught cos phi naught. We know all data, so it will be 0.48 ampere. And the magnetizing component I mu will be equal to I naught sin phi naught, which comes to be 1.44 amps. Now just have a conclusion that the iron loss component of the current is much lesser compared to the magnetizing component. So you will be always having that the magnetizing component will be very, very high as compared to the iron loss component. So here on an average, we are having 3 and 3.5 times more. That is the magnetizing component, because the current I mu is responsible for the production of the flux in the core, and IW is only representation of the core loss. So when we are drawing the phasor diagram, this I naught component, the slope is inclined towards the I mu side. Okay, so that it will be not like this. So you can see the inclination of the I naught component. It will be more towards I mu side, because I mu has to be more than IW. The third part of the transformer fundamentals we will take on the transformer on load, and when the transformer will be on load, then copper losses will be there, and we have to obtain the equivalent circuit parameters of the transformer. So let us see the problem number 6, where we have 6600 by 400 volt transformer. The primary resistance, so we have been given the value of R1 2.5 ohms, and the reactance on the primary side, so X1 is also given 3.9 ohms. The secondary resistance R2 and the secondary reactance X2 is given. Determine the equivalent circuit parameters referred to the primary side and the secondary side. So in theory, we have seen that we can obtain the equivalent resistance, equivalent reactance on the primary side, and we can obtain the equivalent resistance and equivalent reactance on the secondary side. So let us see how we can do that. So first we are going to note all the data that are given to us: E1, E2, the primary resistance, the primary reactance, secondary resistance, and the secondary reactance. So the transformation ratio K, which is the secondary EMF by primary EMF, comes to be 0.06, and hence the value of the resistance on the primary side, equivalent resistance, we can say that it is equal to R1 plus R2 by K square. So all the data are given. We will get 5.28 ohms. This is the total resistance on the primary side. Similarly, the total reactance on the primary side, X1 plus X2 by K square, comes to be 10.84 ohms. When we refer this quantity to the secondary side, we know that when we refer primary parameters to the secondary parameters, we have to multiply with K square, the resistance and the reactance. When secondary is referred to the primary side, we have to divide with 1 by K square. So here we can find the resistance on the secondary side and the reactance on the secondary side by multiplying with K square term in the parameters that we have obtained, R01 and X01. So that will give 0.02 ohms and 0.04 ohms. Now, next problem, 7th problem, where we have a 30 kVA 2400 by 120 volt 50 Hz transformer, has a high voltage winding resistance of 0.1 ohm and leakage reactance of 0.22 ohms. The low voltage winding resistance is 0.035 and the leakage reactance is 0.012. Calculate the equivalent resistance as referred to the primary side and the secondary side, equivalent reactance as referred to the primary and the secondary, and the impedance also. So we know that the impedance is basically R plus J times the reactance X. So we have to determine the total resistance, total reactance, and the total impedance both from the primary side and the secondary side. We have to determine the copper loss also at the full load condition and 75% of the full load condition. So all the data that are given to us, let us first note down. So the kVA rating, the resistance of the primary, reactance of the primary, the induced EMF of the primary, induced EMF of the secondary side, the reactance on the secondary side and the resistance on the secondary side, all are given. So once we are noting these values, first we have to determine the transformation ratio K, which is equal to E2 by E1 comes to be 0.05. Now the resistance, first we will determine from the primary perspective. So R01 is equal to R1 plus R2 by K square, which comes to be 14.1 ohms. Now R02 we can refer, that is primary can be referred to the secondary side multiplying with K square. So that is 0.035 ohms. Similarly, the reactance on the primary side is equal to X1 plus X2 by K square, which comes to be 5.02 ohms. And the reactance on the secondary side is K square multiplied with the reactance on the primary side, which comes to be 0.013 ohms. Now, we can determine the impedance Z01, which is under root of R01 square plus X01. So we have obtained the value of R01. We have obtained the value of X01. Hence, we can obtain the impedance Z01, which comes to be 14.97 ohms. We can obtain the impedance on the secondary side, which is equal to K square multiplied with the impedance on the primary side, net equivalent impedance, that comes to be 0.037 ohms. Now we have to determine the copper loss under the full load condition and also 75% of the full load. So taking the ideal transformer into account, E2 is normally equal to V2, which is equal to 120 volt. And the secondary current which is flowing here is kVA rating multiplied with 1000 by the secondary voltage. So 250 amps is the current which is flowing under the full load condition. So the copper loss under the full load condition we can find as I2 square multiplied with R02. So the current we are taking as the full load current and the total resistance we are taking on the secondary side. If we are calculating I1 square R01, that will give the same answer. Or if we are calculating I1 square R1 plus I2 square R2, that will also give the same answer. So copper loss we can calculate either from the secondary side equivalent parameters, primary side equivalent parameters, or we can calculate both separately from the primary side or the secondary side. So that will equal to 2.818 kilowatt. So this is the copper loss under the full load. When it is in 75% of the full load, 75% of the full load means 75 by 100. So this is the loading on the transformer X, and the copper loss is a variable loss. So copper loss under the 75% of the full load condition, we will get X square multiplied with copper loss under full load condition. So full load condition, it is 2.18 kilowatt, and this will be 0.75 whole square. So which comes to be 1.23 kilowatt. Note, iron loss is a constant loss which will never change irrespective of the loading condition. But copper loss under different loading condition will be equal to X square multiplied with the copper loss under the full load condition. The next part of this tutorial will be focusing on voltage regulation. We know we have seen in the lecture class that voltage regulation is basically E2 minus V2 by E2 into 100. So no load minus full load, this is no load, this is full load, this is no load into 100. That is the voltage regulation. And the voltage drop E2 minus V2 we can calculate from the equivalent circuit parameters. So the problem number 8, where we have a single phase 440 by 220 volt 10 kVA 50 Hz transformer, the resistance of 0.2 ohm and reactance of 0.6 ohm are on the high voltage side. So high voltage side is basically 440 volt side. The corresponding values on the low voltage side is also given. So 220 volt side is also given. Calculate the percentage regulation on the full load side or the full load condition for 0.8 lagging power factor, 0.8 leading power factor and unity power factor. So under different power factor condition, we have to find the percentage regulation of the transformer. So given the data, kVA rating, the secondary EMF, primary EMF, the resistance of the secondary side, primary resistance, the reactance on the secondary side and reactance on the primary side. we will take V2 equal to E2 in terms of the ideal transformer. And then the current on the secondary side we can find as the kVA rating multiplied with 1000 by the secondary voltage, which comes to be 45.45 amps. The transformation ratio K is equal to E2 by E1, which comes to be 0.5. Hence, the parameters R02 and X02 we can calculate from the secondary perspective, that is the equivalent circuit parameters, which is R2 plus K square R1, which comes to be 0.09 ohms, and X2 plus K square X1, which comes to be 0.29 ohms. First, we will determine the regulation under full load condition for 0.8 lagging power factor. Now, the power factor is lagging in nature. Cos phi value is 0.8, hence sin phi will be 0.6. How? We first compute the value of phi, which is equal to cos inverse of 0.8, and then we can put it sin phi. So we get 0.6. Percentage regulation, we have seen in the lecture that it is equal to E2 minus V2 by E2. And this E2 minus V2 is the voltage drop, which in terms of the parameter we can write as I2 R02 cos phi plus X02 sin phi divided by E2. Note here, plus sign we are using because the power factor is lagging in nature. So all the datas are given. So we'll substitute the datas. The regulation will come 5.08 in plus. When the power factor is leading, then in that case, only negative sign will come in the formula of the voltage drop. So here, when we substitute the values, whatever is given, we can calculate the regulation. Note that we are getting negative sign in the voltage regulation when the power factor is leading in nature. Now for unity power factor, where the cos phi value will be 1, sin phi will be 0, then in that case, the voltage regulation can be computed from the plus or minus point. It comes to be 1.86% as the percentage voltage regulation. So that is for unity power factor. Next topic we are going to take from the efficiency point of view. So we will take the iron loss and the copper loss and determine the efficiency. So first problem, or the problem number 9th in this tutorial, we have the iron loss when the rating of a transformer is 80 kVA, 1000 by 250 volt single phase 50 Hz transformer is 500 watt. So this is the iron loss. Note, iron loss is a constant loss. It will never change with respect to the load. The full load copper loss is 400 watt. So 400 watt is basically the copper loss of the transformer when the full load current is flowing. So if 80 kVA transformer is there and we are computing it from the 1000 volt side, then we can find what is the full load current. So that is giving the full load copper loss 400 watt. The area of cross section is given for 1 Tesla and 1000 turns on the primary side. We have to determine efficiency at full load and power factor at 0.8 lagging. We have to determine, and also when the loading is 75% of the full load and unity power factor, we have to determine the efficiency. So when the loading change, obviously the copper loss will change. So first we will note all the data that are given to us. So especially here to be noted is that iron loss is 0.5 kilowatt. So we have converted that into kilowatt. So 500 watt is equal to 0.5 kilowatt. And the copper loss under full load condition is 0.4 kilowatt. So here 400 watt is given. And other data are as usual. So we can find the area of the cross section of the limb first from the EMF equation, similar to the first problem of the tutorial, which gives the area of the core is 4.5 into 10 to the power minus 3 meters square. Next, when we are computing the efficiency at full load and 0.8 lagging power factor, if it is under full load, then X will be equal to 1 and power factor with cos phi will be 0.8. Now efficiency formula in general for all loading condition, we can use this formula X into full load kVA multiplied with power factor, that is the output power, and here we have this one is the output power plus the iron loss and plus the copper loss under different loading condition. So if the loading is X, obviously the power loss in copper side we have to multiply with X square, and iron loss is independent of the loading. So the first problem where the full load is there and power factor is 0.8, we will get 98.61% of the efficiency. Transformer are the most highly efficient devices in the entire electrical machines. So here the efficiency will come more than 95 to 98% will usually get in the problems. So here 98.61 we are getting under the full load. Now when the loading is 75% of the full load, then the copper loss will change. So copper loss will be 0.75 square into 0.4, and the output power will also have a factor of 0.75. Now note here the iron loss is not changing, which is equal to 0.5. So efficiency is 98.81% under 75% on the full load at unity power factor condition. Problem number 10. We have a transformer 150 kVA single phase. Iron loss is 1.4 kilowatt and the full load copper loss is 1.6 kilowatt. Determine the kVA load for the maximum efficiency and the maximum efficiency at 0.8 lagging power factor. So if we are connecting load on the secondary side of the transformer ZL, then what is the kVA of this load so that efficiency is maximum for the transformer? This is the first case. Second case is that what is the maximum efficiency when the power factor is 0.8 lagging of the load? Third, the efficiency at half full load and 0.8 lagging power factor also we have to determine. So first, the given data are full load kVA, the iron loss and the copper loss. So we know that the load kVA for maximum efficiency, load kVA is equal to full load kVA multiplied with the condition of the transformer maximum efficiency. We know that when iron loss is equal to copper loss, then the transformer efficiency is maximum. We also know that when, and this will be equal to the I square multiplied with the resistance, the total resistance. That is, we have either we take I2 side or I1 side. So load kVA will be full load kVA multiplied with under root of iron loss by copper loss. So this means 150.31 kVA has to be the load kVA when the efficiency will be maximum. And the efficiency maximum, we know iron loss has to be equal to copper loss. So that is equal to 1.4 kilowatt. Power factor is 0.8. Hence we can put it in the efficiency formula and find out what is the efficiency of the transformer. That is 97.57%. So all the data are given. Now note here this is iron loss and this is copper loss. And we know that copper loss has to be equal to iron loss for the efficiency maximum. We cannot change this one because iron loss is always a constant loss. The copper loss is a variable loss which will be equal to iron loss. So that will be 97.57%. When the half full load is there, obviously x square copper loss term will come, and here also x will come because the loading is half. So copper loss will change, loading will change, output power will change, and the efficiency will be 97.08%. This is the last part of the tutorial where we will be dealing with open circuit test and short circuit test, determine the parameters, voltage regulation and efficiency we will compute. So in a certain transformer, which is a 5 kVA 200 by 400 volt 50 Hz transformer, the testing has been done, open circuit test and short circuit test. Open circuit test has been done on the low voltage side and short circuit test has been done on the high voltage side. Means all the meters are connected here. So the readings, whatever we are getting, the voltage rating, the voltage, the current and the power. This is what we got it from the open circuit test and the short circuit test. We have to determine the equivalent circuit parameters. We have to determine the efficiency and the regulation and 0.9 power factor leading condition and the rated load. We have to find what is the current at which the efficiency is maximum. Let us see the solution. First, note down the open circuit test data. All the meters are connected on the low voltage side, that is the primary side of the transformer. So we are getting the input power. Note down, this is the iron loss, the voltage on the primary side and the no load current. So these are the data we obtain from the meter. First, we will determine the no load power factor, which is equal to the power divided by voltage into current. That gives 0.43. So if cos phi is 0.43, sin phi will be 0.9. Now we will determine what is IW, that is equal to I naught cos phi naught. That comes to be 0.3 amps. Now we know that in the shunt parameter, this we have discussed in the theory. So here we are having in the shunt parameter, we are having this one is R naught and this one is X naught. And the supply voltage is given here. the no load component of the current I naught is divided into two components. One is the IW component and this current is I mu component. So IW we have computed I naught cos phi naught. R naught when we are computing, then from Ohm's law this will be V1 by IW because these two are in parallel. Similarly, I mu will be I naught sin phi naught and X naught will be V1 by I mu. So these are basically the parameters which we need to compute as the shunt parameters from the open circuit test of the transformer. Now when the transformer is under short circuit test, so short circuit power, short circuit voltage and the short circuit current we are getting. So the first thing that we need to calculate is what is the total impedance, that is voltage short circuit by current short circuit, that gives to be 1.375 ohms. Then the total resistance we can get from the power formula. We know that power is equal to I square R. So resistance will be power divided by I square. So that gives 0.47 ohms. And the reactance will get under root impedance square minus the resistance square, which gives to be 1.29 ohms. So we have to compute these parameters only when the transformer is under short circuit test. Now, since short circuit test we have computed on the secondary side and OC test we have computed on the primary side, so we have to refer to one of the side. So transformation ratio is 2 here, and the total resistance when referred to the primary side is R02 by K square, and the total reactance referred to the primary side is X02 by K square. Now this is the equivalent circuit of the transformer when referred to the primary side. So we have referred the transformer to the primary side. This is the value of R0, this is X0, this is R01, this is X01. And whatever the load we are taking on the secondary side, that will be referred on the primary side also. So it will be ZL dash. We are not caring on this load, we are caring only on the equivalent circuit parameters. Now, the efficiency we need to compute at rated load and 0.9 power factor leading condition. So, iron loss is 60 watt and the total current which is flowing on the secondary side is 12.5 amps that we can compute. So, the copper loss under the full load condition is I2 square into R02, which comes to be 0.073 kilowatt. Hence, when the loading is full load and the power factor is 0.9, we can use the efficiency formula. Here X will be equal to 1 and the copper loss we have to compute at the loading condition. However, since the loading is full, we need not to worry, we can directly substitute the value of the copper loss. So that is 97.13%. Now regulation we have to find at rated load and 0.9 power factor leading. So cos phi is 0.9, that is the power factor, and sin phi is 0.44. So percentage regulation formula which we have used, here we have a negative sign because the power factor is leading. So this is the voltage drop I2 R02 cos phi minus X02 sin phi, and the base is E2 we are taking to determine the percentage voltage regulation. So voltage regulation is coming minus 0.45%. Now the last part of the question, it was asked what is the current and the maximum efficiency. So the condition of the maximum efficiency when we say that iron loss is equal to copper loss and this copper loss is equal to the current square multiplied with the resistance. So total resistance we are taking, and hence we can say I2 square R02. So from here we can find what is the current of maximum efficiency under root of iron loss divided by the total resistance. So that gives 11.3 amps as the total current on the secondary side when the efficiency is maximum. So we have splitted this tutorial problems under different sections and computed the problems. You watch the lecture series, which is 3 parts are there in the lecture, and those lectures will help in understanding this tutorial well.